Hi everybody, thank you for listening to our talk today. I'm Emily, I'm Coastal Engineer at the Operations team at Coastal Partners. This piece of work has been led by Andy, Sam and myself with HR Wallingford carrying out the statistical modelling. We have recently been rebranded from Eastern Coastal Partnership to Coastal Partners. This reflects our values and our visions to partner with groups beyond the four founding local authorities. To give a brief introduction to the area, Hayling Island is sat on the south coast, just between Portsmouth and Chichester. And the southeast corner that we're just overlooking here in the image is called East Stoke, and that's where our study is focused on. So Hayling Island in general is exposed to energetic swell waves that travel up the channel from the Atlantic. And even though it sits in the lee of the Isle of Wight, wave refraction does mean that it can take a bit of a battering during stormy conditions. This slide just shows the latest Environment Agency flood mapping from 2020, including all the latest modelling. The light blue area depicts a 1 in 200 year risk of flooding. And at this location, we've got lots of low-lying land. The significant threat here is the wave overtopping rather than the still water level. The image on the left-hand side is from approximately 1970, and that was before the capital dredge took place at East Stoke. So as East Stoke became more and more developed, the seawall was built to protect the properties. Beach load in front of this led to the need for several repairs. And eventually the beach lowered so much that sand and the clay bed became exposed. And this bed lowering led to significant overtopping, which can be seen in those two images there. So waves are able to break directly over the sea walls, they impact the first line of properties, and further beyond that into the low-lying areas of East Stoke. At this point, we're probably experiencing annual flooding, and more often not, properties were affected. To address this, in 1985, approximately £4 million was awarded to Havant to create the large shingle beach that now acts as a primary defence there at East Stoke. So over 500,000 metres cubed of material was dredged and placed onto the beach. And as with all beaches that are primary flood defences, it's required regular maintenance to keep it topped up, and currently we do intervene annually. The current BMP that's in place runs from 2017 to 2022, and £3.3 million of grant and aid funding from the EA was awarded to reduce the risk to over 1,500 properties at East Stoke. It includes a combination of beach recycling and periodic recharge as well via beach renourishment. Material is picked up from places it naturally accretes, so for example the open beach and Gunner Point. And there's also the occasional requirement for imported sorter material or a dredge from an offshore licensed site. The drift divider at East Stoke at Creek Road Car Park is a significant erosion point, as well as East Stoke Corner, and both of these are just addressed by the BMP. The funding that was awarded it allowed us to do several studies to better understand the coastal process along Hayling Island and better understand what's going on. And this just leads to efficiencies in how we can then manage the beach. And of course, one of these studies is the bimodal wave study. The current design profile is 18 metres wide and 5.6 metres high, but this has been in place since 2004, and it was designed only accounting for unimodal waves. This slide just summarises some of what we were experiencing in more recent years. So the graph on the top left shows the occurrence of flooding at East Stoke since the 1960s, and severity 1 here is sort of flooding of open areas, the prom, but we don't experience any structural damage or real disruption. And that goes all the way up to severity 5, which is flooding over large areas. Emergency services would usually be required and significant pumping. And we say here that if more than 15 properties are affected, then it falls into that category. The increase in 2005 is partially due to methods, but we are seeing this on the ground. And the emerging evidence from the Scopac storm analysis study is also suggesting that we are having stormier recent years. These two photos on the right-hand side just show some on-the-ground examples of the typical response and the damage that we can get where the crest rolled backwards onto the prom and the waves are able to rush over. As a rough guide, the horizontal part of the groin should be covered when the beach is at its design. And the bottom photo just highlights how quickly the crest can become depleted in just a single event. And we've had a number of events at East Oak which shouldn't have caused this much damage when we're looking at the traditional methods of looking at storms just according to their wave height thresholds. What we found is these storms have actually got a lot of their energy from swell waves, which cause increased erosion. And then when these swell waves combine with the locally generated storm waves, we experience bimodal sea conditions, and that compounds the problem even further. So the graph on the bottom left shows the increasing magnitude of swell events. We're getting many more longer period swell events since the 2013-14 winter. And the hailing wave buoys has provided valuable insights here on the wave climate, and we're able to pick up these trends over time. And since 2003, we've recorded the highest significant wave height recorded at hailing, as well as the highest percentage of bimodal seas recorded in a month, and the stormiest season since recording began in 2003. Bimodal seas are experienced when there is a mix of offshore generated swell waves, which tend to have longer wavelength but a lower steepness, and locally generated wind or storm waves, which have a shorter wavelength but are steeper. And that's just illustrated on the left-hand side there. This gives two distinct peaks on the energy spectrum for the two wavelengths. And there's just a sample there on the right-hand side from the PCO wavebuoy network. And by definition, a bimodal sea state should fulfill the four criteria that are just listed on the slide there. Not a huge amount is known about the effect of bimodal seas on beaches and coastal structures, as usually the wind and the swell waves are considered separately in design assessment, rather than both at the same time. But this is certainly beginning to change. However, it is recognised that bimodal seas may represent worst case conditions for shingle beaches. So these significantly impact on pore pressures, influencing wave run-up, that then influences overwashing and hence influences the standard protection at East Oak. So extreme conditions are very important for design. Joint probability gives the likelihood of two or more extremes occurring together. So for example, significant wave height and water level, and the more traditional design criteria is based on that. So we commissioned HR Wallingford to produce new joint probability return periods that incorporated bimodality using the wavebuoy data, and this results in multivariate analysis. This will be a very light touch on the statistical modelling. This was all done by our consultants and is not my area of expertise. It was all carried out using wavebuoy information. This allowed the two-tail wave spectrum to be analysed, broken down, split up into their constituent parts. And the study aimed to define a single quantity to represent the beach response to the return period. So here we've used overwash potential and the crest position. Those were both deemed sensible. And from these, a composite response index, or CRI, can be formed, and that gives an approximate univariate beach response. It allows a subset of the data to then be taken forward for statistical analysis. A distribution curve can be fit to the CRI of observed data, which then corresponds to return period, and then that can be extrapolated by then synthesizing more extreme events to develop a population for each variate. And by stacking these variates on top of each other, we can sample the population for combinations of conditions that lead to those extreme beach responses and therefore put a return value on them. So we end up with an extreme wave condition for our typical unimodal wave conditions, and another set, a different set for the bimodal wave conditions. This slide just shows some of the results produced by the study. They're logical, they feel about right when we consider that the highest significant wave height recorded was 4.4 metres, and that was for a unimodal wave event. So 1 in 200 year wave heights for the unimodal table are higher than 4.4 metres. This wave height does appear in the bimodal wave table as a 1 in 200 year condition, but of course the bimodal component is considered here. For context, the most recent annual wave report from CCO put an estimate of 1 in 50 years for a return period of a wave height of 4.4 metres. If we match up similar wave heights and water levels of the more traditional joint probability analysis, we can see the effect that bimodality has on the return period of these events. So the red pair and the yellow pair are matched as well as possible, in terms of their water level and their wave height. But they show significantly different return periods. And this highlights how important that, that swell bimodal component can be. In response to a lack of understanding of the impact of bimodal wave on shingle beaches, Shingle B was developed. So this was then used to test the design profile, or the current design profile that we've got at Eastock. And just on screen here, we can see the results for a 1 in 200 bimodal event. The spike here is assumed to be the volume of material that is pushed back into the prong, as we saw in some of the previous photos. The results show that under all the 1 in 200 year bimodal conditions, the crest is severely cut back. This exposes the seawall, and the potential for wave overtopping is a lot greater, and we end up in a situation much more similar to that we were in pre-1985, before the capital recharge. It appears our design profile withstands unimodal conditions better, but in terms of erosion doesn't necessarily stand up to a 1 in 100 year bimodal event. So we can see that it's something more similar. It stands up to something more similar to a 1 in 75 or 100 bimodal event. And that's just in terms of erosion and crest cutback. So for all our return periods, the bimodal results produce a worse outcome than for the unimodal events. But we do need to understand the overtopping aspects here. Peak conditions for beach profile erosion may not be the peak conditions for wave overtopping. So it's a complex problem, and something that we're going to be exploring over the next 12 months. The PCO wave data has been invaluable in carrying out this piece of work. And we have found that bimodal waves do result in a greater impact to the beach than unimodal waves. Profile and topographic data has been equally as important, so that we can measure these responses to these conditions. We'll be carrying out further investigation to assess the standard of protection of our beach, and the strategic decisions here on how to manage the beach are going to be made through the Hailing Island strategy. Thank you very much for listening.